Hello everyone, welcome to another video. So oftentimes we have models that are kind of an assembly of different models imported into one, and so here we have I think five different models. So you have this coupler which was copied to this. Okay, you just have four couplers and then they are separated, and then you have the main cavity. Now, if you should observe very well, you have that at some point in time the coupler overlaps with the coupler model overlaps with the cavity for all four couplers. Now, the question is usually, or one question is, or one question that I explore, the question I explore in this video is how does it affect the mesh or not? So that's what I'm looking at, having such overlaps. Now, because they are the same material, so it's vacuum, and then the cavity material is also vacuum. So because they're the same material, CST only gives you a warning. I wonder why there's no warning here. Normally there's a warning that, okay, you have these overlapping regions, and then it mentions the devices that you have the overlapping regions. So it gives this warning. But then, since if it's the same material, if you apply exactly the same material, it does not lead to any error, and your simulation, your mesh is generated, your simulation runs smoothly. But then I also have this model here in which I combined the overlapping parts. So you see there's no, so if I should go for the coupler, you have just the coupler itself, and then there's just the antenna of the couplers. So if I should select all the four couplers, you see just the antennas, and then you have the other vacuum element. So the vacuum materials combined into one big elements. Now, what we'll be looking at today is how the mesh differs between these two models and if it affects the results or not. So if you go over here, down here, we can see it, the mouse. You see that you have the number of tetrahedrons. So it's exactly the same geometry, nothing changed. But then you see that the mesh here has 150,333 tetrahedrons, and then for this is 147,838 tetrahedrons. So the mesh generated is clearly different from the number of tetrahedrons that you have generated. Whether when it's separate, whether the mesh is the tetrahedron number of mesh elements is always more when it's separated or not, I do not know. I haven't checked for many cases, but probably most like, okay, I wouldn't make any statement on that, because I think I could imagine some scenarios where it is more for when you combine the geometry. So that's one difference, and then in a second we'll see how it actually affects the results, if it affects the results very much. But then first of all, let's look at the mesh. So if I should go to the mesh view, this is what I have, and then you would see, let me see, you would see that this is what the mesh looks like. So I'm going to look at exactly the same part on the combined assembly. So this is what we have. So you could clearly see that at this point where there is a difference, although CST looks at the combined part as one because it's the same material, you see that the way it goes about generating the mesh is different. So I think that it takes this region, so the coupler region, as it looks at it as kind of maybe a different, where am I? No, this is a mesh view. So we have this coupler, and then we have this overlapping region. So I do not know the meshing algorithm, so I can't really say so much on it. But then it looks as if it's it generates the mesh in this region kind of differently, or and then considers this tiny part. So there's a space in between the end of the cavities and the mesh. So you also see that the mesh is generated here. Now, depending on what, and then for this you don't see it, so it's just continuous around this point. So I think depending on your model and geometry, this might actually affect the quality of your mesh, maybe adversely or not. I mean, in this case I run, when we look at the results, we see that there are some differences, but then for me it's not. There are some differences in different for different post-processing results that I evaluated. So we'll see it, and then for I think for your geometry or your assembly or your model, you'd have to kind of think about it, take that if it's something that would affect your result or not, and then that's combining the mesh or leaving it like that. And I would also give one thing I found useful in leaving the model not combined. So, but first, let's look at the results. So for the results, I compared the frequency of the modes, and then in the previous video, I copied this result into this, so I have an easy comparison. So this is what I had. So for the frequency, you see that between the two meshes, so the red is combined and then this is separate. So you see that you have, for the first mode, you have just a tiny difference, negligible difference in frequency. For this also, you have kind of negligible difference, and then 793.08 up to the second decimal you have correspondence, good correspondence, and then for these two you have good correspondence up to the second decimal, and then the trend is kind of continued for all frequency. However, if we compare the external quality factors, then we see some difference between the values calculated, although kind of yeah, a caveat: the modes that I'm looking at here, they do not propagate into the beam pipe, so depending on the length of the beam pipe, you could also have different results. However, for exactly the same model, we see how the external quality factor could vary depending on if you um, combine your different parts of your model. If you should combine everything into one big and combining, I mean, just using your Boolean operation. You should combine everything into one whole model. That is for the parts that are similar, that have similar materials and overlap. You should combine them versus if you do not combine them. So you see the external quality factor difference. It differs. So for this, you could have as much as an order of magnitude, or is it 2 orders of magnitude? This is, so let me log it so we could see it better. Yes. So we have that this is roughly an order of magnitude difference in the external quality factor. Then for this, you have okay, not so much, just a three times difference, a factor of 3 difference between them. And then for this, you also have, I think, so this is 2 and then this is 2. So this is also an order of magnitude difference between the results. Now, this would also translate to the other results you would use your external quality factor to calculate. So for example, I would also want to compare the R over Q. So if I should copy this, then I would go here and then right click and create a new folder tree, so R over Q, and then I would paste this with prefix, and then this is for the combined. Yes, then I copy the same for this, paste with prefix, suffix, and this is separate. I spelled that correctly. Yes, so for the R over Q, you have that the values are also not very different. So this is 1.19, 1.18, this is 0.004, 0.003. So this is different. So you could see that in some places there are subtle differences, and then also have in mind that I'm just looking at 5 modes. Probably for some modes the difference might be more drastic than these ones I'm just looking at, so just pointing that out. Now R over Q, okay, we won't say it's as drastically different as the value for the external quality factor, also for the frequency. Now if I should look at the impedance, which is calculated using the R over Q and the external quality factor, I would copy this, and then let's create a new folder tree, and then I call it Z kilo ohm. Then I paste this, and then this is combined, and oh, I would have put an underscore, but no matter. And then I copy this Z, and then this is separate. I think I should put an underscore. So for this, you could also rename it. So I could put an underscore combined, and then I put an underscore separate. Yes. And then click on it. Now you could see the difference, and then this difference is because of the, so you see the difference between the impedance, the calculated impedance from the external quality factor, and then it's about 1 order of magnitude. It's a 1 order of magnitude difference. So, but then for some other modes, it's not that drastic. And then this difference is coming from the external quality factor. Now let's look at one more before I call it. So, although I think that it will be the same. So let's look at the transverse R over Q. So if I should copy this and then create a new folder, I could just put it in this folder, R over Q. Paste with prefix combined underscore, and then I copy from this R over Q to copy, and let's see, paste with prefix underscore separate. So we also see that there's a big difference between this the values, although for this the difference could be explained by something else, because no, it shouldn't vary that much. I mean, I was looking at the orientation of the field um, between, that's the calculated field for the two modes, for the two different setups. But then this is the monopole mode, so there's no difference in polarization, so it should be the same. But then you see that there's a lot of difference. There's also a lot of difference between these. So I mean, more than an order of magnitude between the transverse R over Q calculated. So this just shows that it actually makes a difference. Now, as to which is more accurate, one would only know by doing a convergence study using the two. So the settings for the mesh, I'll just show it, is 10 cells per wavelength for both combined, and so for both setups it's 10. So exactly the same setting, exactly the same settings for, exactly the same mesh settings, exactly the same solver settings for the two models, but then we have such different results. So it's just something to have at the back of your mind when running your analysis, especially when you have different models. The only way to actually know which is more accurate is to do a convergence study, which I hope to be doing for the two models, and see if the results converge to exactly the same thing for both combined and also separate. I mean, I would expect that they converge to exactly the same values for both cases. So just pointing out something to keep in mind when analyzing your result, and when setting up your geometry. So yeah, that was it for this video. And I also checked for the hexagonal hexahedral mesh, and then you see that you have the same difference in mesh cells. So for your mesh cells, I think I could view the mesh. Yes, for both cases. So this is when you do not combine the overlapping parts. You have 471,774 mesh cells, and then for this you have 454,896,000 mesh cells. So you also have a difference for the hexahedral mesh. I was thinking that it would not be so different because of the way the mesh is generated, but then it's still the same. So there's still a difference between the mesh, and then this would go ahead to affect the result. How much it affects the result, I did not check. You could check that on your own. But then I think in a future video, or I hope that in a future video, which would be kind of a part 2 to this, I would do the convergence study to see how well these values align when you keep increasing the mesh resolution, or you do an adaptive convergence study. So yeah, that was it for this video, and I hope it's useful. Yeah.